So, hi, my name is Tomáš Vondra. I do work for EDB. I'm a long-term contributor, developer, and also a committer. And I'm here to talk about performance cliffs, which is a performance issue affecting a lot of people that may not be aware of that. I'm going to explain how the performance issue actually happens and why. I'm also going to mention a couple ways to maybe reduce the impact of the issue and maybe present a couple ideas for future development and how to improve that in the future. Right. So, as I mentioned, I work for EDB, and the quick agenda for this talk is brief explanation of what the performance cliff issue is about. It's actually a pretty common issue, but it's somewhat hidden. It's not very obvious or may not be very obvious. And it's kind of inherent to all cost-based planning, right? So kind of all databases that do planning based on cost estimation are affected by that. I will explain why it happens and then give a couple suggestions for improvements. So first of all, like what actually is a performance cliff? There are probably different ways to define that. I say that performance cliff is a sudden, like a step change in performance. So sudden means not proportional to inputs, right? So for example, if you consider a query, as for example on the slide, which may return 1,000 rows, and it takes only like 1,000 seconds. What if, how long should it take actually to return 1,001 rows, right? I mean, like, if it takes roughly the same amount of time, because it's like less than 1% of difference in the cardinality of the result, that's probably okay, right? But maybe it will take 10 seconds, right? Which is like sudden change, unexpected, based on the change in the parameters. So, and that's what I call a performance cliff, right? Step change in performance. So to explain how the performance cliff can actually happen, I need to kind of like explain how databases do planning based on cost. A cost is just an approximation or like some sort of number that explains how many resources or how much resources will the query need to execute. And by resources, we mean usually like CPU and I/O. And the whole idea of cost-based planning is based on the assumption that if a query needs more resources, like more random I/O, for example, that means higher cost, and that will take longer to execute, right? So the assumption about cost is that it's monotonic and continuous, right? So it changes like gradually, that's the continuous thing, and that it's monotonic, which means that the more data you need to process for a query, the higher the cost, and also monotonic with respect to duration of the query. So if you have a higher cost, it will mean that the query takes longer, right? And we kind of, for the purpose of this talk, I will assume that the estimates, the cardinality estimates are correct, right? I mean, there is a whole class of performance issues about incorrect estimates. I'm not going to talk about that at all. I'm going to talk about issues where we actually know how much data are going to process within some reasonable margin of error, but then do like mistakes during planning later. So to visualize how the cost actually behaves, you can do a very simple thing. I have a query here, and I change the input parameters of the query slightly, right? I know what fraction of the rows will actually match, and that's determined by the condition of the query. And then I can, for each query, measure two things. First is the cost, which is in the first line of the execution plan. So in this case, it's about 24,091. That's the cost estimate for the query. And then we also, if you run the query, you can actually get the timing of the query, right? So in this case, it's about 72 milliseconds. And if you do this for a range of parameters for different fractions of the table, different conditions, essentially, which in this case is 1%, but you can change the parameters to get like different results, you will get a table which is shown on the slide. Obviously, for your query, the conditions or the values will be different, right? But you can take the table and you can actually visualize it as a chart, right? So in this chart, on the horizontal axis, on X, that's the selectivity, like the fraction of the table that matches the condition, right? So it's between 0 and 100%, roughly. And then the blue line is the cost, which is estimated by the database, like estimate of how much resources will be needed to execute the query, and then also the duration, which is the actual time that took to execute the query, right? And you can see that it's more or less monotonic. There's small calculation issue for the cost, close to like 0% selectivity. But other than that, it's very continuous, and it's also correlated to the duration. It's nonlinear dependency though, so it's not very easy to actually, calculate the estimated time from the cost, right? So that doesn't actually work very well. So this is what the database actually uses to pick the cheapest plan, right? And that's a bit weird though, right? Because I started this by defining the performance cliff as a discontinuity, like a sudden step change in the query plan, right? And the chart that I just showed is actually perfectly continuous and mostly monotonic, right? So where could we actually get like discontinuities, like step changes in this? And there are like two basic ways how we can actually get that. The first one is related to things decided at the runtime, right? So those are like decisions when, if you process just a little bit more data, like one more row, it flips some algorithm or something to slightly different behavior, and that can actually change the performance. The other problem that we have, and I'm going to talk about that later, is having to deal with multiple different paths, different execution plans, right? The chart that I showed is just for a single type of scan of a table, but you usually have like many different ways to run the query, and the database needs actually to change between the plans for different selectivities, right? So first, let's talk about the runtime decisions. And I'm going to illustrate that by a very simple example. Imagine you have a query which is simple sequential scan from a table. There are no indexes on the table. The table has about a gigabyte of data in it. And you do select on that with a condition which is an in condition, which means the column needs to be one of the values listed in the list, right? And I'm going to show the timings and everything using a table which has some random data in it, right? The only thing here is that it's about 10 million rows, and all the strings have fairly long prefix, which is just the character A, right? So if you do this, you can try that after the talk. You should get a table which is about 1 gigabyte of data. And now let's run a query. And the query is very simple. It just has like a list with 9 rows, 9 values. And if you try this, it runs in about a second on my machine, right? Which is fine. That's like a sequential scan of 1 gigabyte of data on like a laptop or something is perfectly reasonable. So nothing wrong with that. Now let's remove one of the values. So we will only have a condition with 9 values. And what would we expect? I mean, like, we are going to evaluate fewer conditions, essentially. And other than that, we will scan the whole table again, right? Still sequential scan. So we probably expect that to take a little bit less time, right? Maybe 900 milliseconds or something like that. But if you try that, it will actually run in 2 seconds. Like, it's actually taking twice as much time as the first query. So that's weird, right? I mean, like, why would this happen? And the reason is very simple. We realize that the list can be quite long, and instead of like doing a linear search through a long list, what we do is we build a hash table, right? And then we actually for the list in the in condition, and then instead of searching through the list and checking all the values, we just do a lookup in the hash table. Perfectly reasonable. However, this is not efficient if the list is very short, right? And by short, I mean fewer than 9 values, which is why I used 9 values in the first query, because that's the case when we actually start using a hash table. So by removing one value, I actually force the database to use a linear search, which is not very efficient in this case. So, and that's why it took so long. The problem with this is obviously it's a decision that is hard-coded. The threshold is not perfect for all possible data types, all possible cases. And it's impossible for the database to know this in advance, right? So there's not much we can do to improve that. Maybe there is a way to make this more adaptive to kind of like respond to the actual execution, but that's not implemented, right? So you can actually run into this. So there are other runtime decisions. This was just a very short example, right? So for example, when you are doing anything that can start spilling data to disk, like a sort or hash join or hash aggregate, for example, that can actually happen unpredictably, right? The database may not actually consider this during the planning, and then realize actually it needs a little bit more data and starts spilling data to disk, which can be quite expensive, of course, right? Another example of runtime decisions is just-in-time compilation, which is decided during planning, but we also don't have a very good heuristics about when it's going to be beneficial and so on. So it can actually hurt the individual queries. And there is an ongoing effort, multiple patches currently in development that should help with this. So now about the other problem, which is about multiple paths. So for this, I'm going to show a different example. We have a table which has about 100 million rows, and it's mostly random, except that it's random for the same value being stored on a single page, right? So we can fit 59 rows on a single page in this case for this table. So we have like 59 repetitions of the same value, which means we are going to select random pages from the table. And with 100 million rows, it's about 13 gigabyte of data, right? And I'm going to use about 10,000 different distinct values, which allows us actually to read a well-known or deterministic fraction of the table depending on the conditions, right? So this is the same chart as before for cost of the queries, using three different scan methods that are implemented in Postgres, which is the regular sequential scan. Then we have the index scan, and we also have a bitmap scan, right? Bitmap index scan. And again, on the horizontal axis is the selectivity of the condition, which means like which fraction of the table are we actually reading, and then on the y-axis is the cost, right? And I'm just going to point that both those axes are log scale in this case. That doesn't really matter, but the important thing here is that the costs actually do cross over at about 1% selectivity, right? Until that point, the index scan and bitmap scan are like the cheapest way to execute the query. And from about 1%, because of the randomness and so on, we actually switch to the sequential scan, right? From that point, it's easier to just read the whole table than using indexes. Well, or at least the database believes that, because if you do the same chart for the actual duration of the query, you will get a very different chart where the sequential scan only becomes the cheapest one, actual fastest query execution, at about 27% selectivity, right? So just to make it more obvious, I left there the 1% from the cost chart, and you can see that there's about like 27% difference between what the database thinks is the cheapest execution and what is the actual cheapest execution, right? And that's a problem, because this means that if you do a query that only selects about like roughly 1% of the data, 1.27%, that runs in about half a second, right? 400 milliseconds is what I got. But if you increase the selectivity of the query by just a very tiny bit, like the smallest fraction that I could in this case, and it's 1.28% essentially, then it suddenly runs in 10 seconds, which is 20 times longer. And that's, again, the performance cliff that I was talking about. And this happens, as you can see from the query, that because the database switched from a bitmap scan to a sequential scan, right? It made the wrong query planning decision. So this is why the database has problems with performance cliffs when using cost-based planning. So what are the ways to actually mitigate this? So first of all, it's really hard, right? It's really hard because it's based on costing, which is an approximation. It's a very simplified model of the data with incomplete statistics that do not have all the details, right? Which inherently means that there's imperfection. And there is a very well-known quote from Götz Greffe which means choice is confusion, right? Once you give the database multiple choices, it will inevitably do some incorrect choices. There's no way around it. And it's not limited just to Postgres, right? Kind of all cost-based databases, or like databases using cost-based planning, will have the same problem. So what can you do actually to mitigate this? Well, for some cases, you can actually just make the cliff smaller. You can either ensure that the flip, like the on-off switch of the runtime decision doesn't actually happen. You can, for example, increase the work mem so that you never need to spill to disk. Or you can actually, if the flip happens, you can kind of like reduce the impact of it. For example, you can use faster ephemeral storage to, if you need to spill to disk, it's actually fast, right? So that's one way to do to improve the situation. For the cost-based performance cliffs, what you can do, well, the only thing you can do at the moment is tune the cost parameters. You can increase the random page cost or reduce the random page cost, for example, and essentially what you are trying to achieve is you are trying to align the crossover points between the different, between the cost and the duration charts. So in this case, you would try to increase the cost, the crossover from like 1% way closer to 27%, right? Which is the actual point where the execution flips to sequential scan, or should switch to sequential scan. It doesn't really matter. It's a lost cause to try to optimize and fine-tune the parameters too much, because the ideal value is probably different for different queries. It just, the flip needs to happen close enough to the actual point. And there are a couple ideas for future development, and some of them are more like research. The first one is adaptive execution. Essentially, instead of relying on the a priori information, like the statistics and so on, too much, we can assume that in some cases it will be wrong, right? And then try to adapt to that during execution, right? So, for example, instead of picking a single way to scan a table, we can kind of like move from index scan to sequential scan, for example, right? And that's the idea behind a smooth scan, which is one of the research papers that I would like to mention later. The good thing is that this is quite difficult, of course, but the good thing is that it would also help not just with these performance cliffs, but it would also help with the cases where we make planning mistakes because of estimating the selectivities incorrectly, right? And it's essentially moving from performance issues into like more robust execution model. And as I mentioned, I do have a couple links to interesting papers, and I'm going to briefly explain what these do. The first one is the profile of Mr. Gefe, one of the people working on robustness in database execution. And he also said that the choice is confusion, right? The two other links on this slide are interesting research papers doing adaptive execution for different types or different operations in the database. The first one is for the scan nodes, so essentially replacing sequential scan, indexing, and so on with a more generic and adaptive access path. And the the last paper does something similar for the join algorithm, right? And on my last slide, I do have a couple links to papers or reports from a seminar, which is exactly about robustness in databases, not just about execution, but about other aspects of robustness. And I think I'm not going to go over the details, of course, but these are, I think, wonderful sources of inspiration, like a starting point if you are interested in this topic. So there's a very nice overview of the problem, and usually links to other research papers that are talking about the same topic. And I think that's all from me for today. And I think I'm ready to take some questions.